This is CS1101 Lecture 12.1. Today we're continuing our discussion of objects. Specifically, we're going to be talking about the this operator more, and we're also going to be continuing to talk about encapsulation, as well as introducing another method which we need to override called equals. First, a little review regarding the this keyword. So it can be used as a reference to the implicit parameter, and the implicit parameter is the object on which a method is called. So if we have a student object called S1 and we say S1.getName, we're calling the instance method getName on the implicit parameter S1, which is an instance of the student class. So we see this keyword used in multiple situations. Specifically, it's optional when we refer to an instance variable in the class, but we've seen that if there are conflicting scopes, so as an example, if we had a parameter called age and an instance variable called age in our student class, then these scopes overlap in a way that is legal in Java. However, to use the instance variable in that particular method, we would have to use the this keyword to be able to tell Java, hey, we don't want to use the parameter, we want to use the instance variable. And the reason is because Java is always going to default to whatever has the narrowest scope with that name. If we wanted to call another method in the class, so if we wanted to, from the getName method, if we wanted to also, for some reason, get the age. So inside of student class dot get name, if we also wanted to look at the age for some reason, we could say this dot get age, and it would pass the implicit parameter to the get age instance method, so that we would be able to call the get age method from inside of the get name method. Another situation where you often see this used would be if you wanted to pass the implicit parameter or yourself as an argument to some other method. So if you wanted to pass S1 to another method from inside of an instance method in the student class, then you could use the this keyword to refer to the S1 student object. Or if you wanted to call another constructor from inside of yet another constructor. So if we have a default constructor, let's say, and we also have a constructor that takes parameters, in the case of student, the student name, age, and GPA, then what we could do is we could call the default constructor just to initialize all the variables, and then use the set mutator methods to change the values. So let's remind ourselves of some of the examples we've looked at. So we looked at, and I just mentioned, if we have an instance variable called age and a parameter called age in this method setAge, Java is going to, in both instances, be looking at the parameter in this statement. This is called shadowing, because the more specifically scoped variable called age is going to shadow or hide the less specifically scoped age. So the parameter is going to hide the instance variable. To avoid this, we would need to use the this keyword. So the correct way to write the code from the previous slide would be, here's our instance variable int age, and then we have the same setAge method, and we have age as a parameter to the setAge method, but then inside the method, what we'd actually need to code would be this.age to tell Java, hey, we want to look at the age instance variable that is a part of the implicit parameter this object, and we want to set that value or assign that value to be whatever value is stored in age. Here's an example of passing yourself using the this keyword. So in this code, what we're trying to do is find the distance from the origin to the point value stored in some point object. So we could do this one of two ways. We could either declare the origin point into a point object P, reference variable, and then use the member method, use the instance method distance to find the distance from the XY location stored in this current point object to the origin, so distance from P to the origin. Or what we could do is we could create a point object and store it in our reference variable P and call P.distance and pass as the parameter, pass as the point object this. So understand what's happening here is this is a method, this is an instance method inside of a point object called dist from origin. And another instance method in the point object is called distance. So this configuration of code is going to find the distance from the XY location stored in this object, which we are currently inside, to the origin. Or we could declare a point object P and find the distance from the origin, which is what is stored in P, to this current point object. So we can either go from the current point object to the origin using just distance of P, or we can create this point object and say P.distance to the XY location stored in this, and in this way find the distance from the origin to this. Both of these are valid code, both will work. Two ways of going about the same thing, but the point here is that this refers to the implicit parameter, which is a point object, and we can pass this implicit object to other methods which accept point objects using the keyword this. Here's an example of using the this keyword to call a constructor from inside of another constructor. So we have defined some constructor that takes a name, string variable, age, integer variable, and GPA double variable as parameters, and initializes these instance variables to those values which were passed into the constructor. And then we also have a default constructor which takes no parameters, so that we can create a student object that takes on just default values. But rather than having to write out this.name equals empty string, this.age equals 0, this.gpa equals 0.0, rather than typing that in, it's a little more elegant to use the this keyword to call the other constructor which accepts 3 parameters and simply pass the default values to that other constructor. So here is a mini exercise to see if you're comprehending and understanding the usages of this. Also, there are errors mixed in which may not have anything to do with the this keyword. So look through this code, pause the video, and annotate wherever you see an error. So let's talk through this. First of all, we weren't properly encapsulating our instance variables. So these should have been set to private. They should have had the private modifier. Next, we have no default constructor. So there should have been a default constructor that accepted no parameters so that we could easily create a default student object. Notice in the declaration for this instance method is on a roll. It should be returning a Boolean value, and the return statement does return a Boolean value. However, it's declared to return a double value. So we incorrectly declared our instance method header. GetAge is actually okay. GetGPA, however, should return a double because GPA, the instance variable GPA, is declared as a type double, and the return type on the method header is integer. So that's incorrect. And then finally, in setAge, we need to use the this keyword in order to tell Java that we actually want to set the instance variable called age, even though there's also a parameter called age. So hopefully at this point it's clear that if a class is properly encapsulated, then it provides the abstraction we were talking about. So the abstraction between the client interface and the details of how that works. And encapsulation is all about protecting the data which is stored in the object and allowing it to be accessed and changed or mutated using accessor and mutator methods. But in addition to encapsulation, this is going to protect an object from unwanted access by clients. So in the case of a bank app that forbids a client to change an account's balance, allows you to constrain an object's state. So we're not going to allow points that have negative coordinates, for instance, possibly, or allows you to change the class implementation without having to change every client program that makes use of that class. So if you've encapsulated your programs correctly, then the user interface is going to communicate everything needed to know to be able to use the class in a client program, while the implementation is going to hide all the messiness and details of how it works and allow you to update this class in the future without having to change all the individual client programs that may make use of the class. Well-encapsulated code typically is better code, and that's what a company is going to want. That's what's going to be expected in a professional engineering environment. Part of encapsulating your programs well is appropriately commenting the code. You should always precede the class definition with a comment or two that's going to shape the programmer's understanding when they go to use the class, and the idea and method behind the design of the class. You should declare the instance variables and any particularly sensitive instance methods private, so that direct access and incorrect modifications to the internals of the object, sort of like the bank account balance, are not possible. And in lieu of giving direct access, you should supply accessor and mutator methods so that you can control what changes to values may be made and how values are read out of the object. In general, beyond just the accessor and mutator methods that you should supply for dealing with instance variables and their values, you should also supply public methods that are going to be necessary for using the class appropriately. So, think distance, right? So in the point object, we have the distance method. Without that, we would not have all the functionality we would expect from a point object. So any functionality that would be expected or implied in that particular type of class, we would expect to see public methods to perform those behaviors. Further, you should use Java docs to explain the functionality of the methods, and this is how you inform users how to use the class. You should, again, set appropriate class methods to private. So if there are specific methods that you only want to be used inside of the class, so that would protect them so they wouldn't be able to be called externally, then they should be set to private. And then remember to comment inside the code, not just above the class and above the methods. Comment the code to clearly explain exactly what your code intends to do and how the functionality is achieved. So what's this all about? Encapsulation is meant to permit implementation changes without requiring changes in any program or class that uses the class. Let's make that a little more clear. Let's say that someone changes the index of method built into the array class. So imagine if you wrote a client program that used the index of method to find the index of a particular item in an array. Then somebody changed the implementation in Java of index of so that when it couldn't find the value you're looking for, it returned 999, whereas right now it would return -1. So that implementation change is going to be very problematic for anybody who has coded a client program using the index of method. Because now whatever code they have written is no longer viable, it's no longer valid. Because they were expecting to see a -1 if index of couldn't find the value in the array, and now it's going to return 999. So their code's not going to work anymore. That's the point of encapsulation. This shouldn't happen. It shouldn't be that changing the implementation of index of changes anything about the user interface. The user interface should be a separate entity from the implementation, and even if we have to adjust to fix errors, the implementation, it shouldn't change how client programs are going to interact with our methods, in this case index of. This is kind of like when, Apple or Windows pushes out, or Microsoft pushes out updates. It would be very problematic and annoying if they fundamentally changed the user interface for their products with each update. No one would want to buy or use their products. So they need to keep the look and the feel of the user interface the same, even if behind the scenes things are changing. And that's the same thing that we're going for with encapsulation. We want to separate the implementation from the user interface so that if we need to change something to update the methods or the class in general, any client programs which are built using this class are still viable and still work. So we won't discuss it at length, but a buzzword to be aware of here is an abstract data type, which is basically the same idea as a well-encapsulated class. Finally, let's talk about the equals method. So remember, when we tried to compare objects using the equals operator, it only compared primitive types correctly. When we compared non-primitive types, if you remember, what we actually wound up doing was comparing the memory locations stored in the reference variables, right? Because the thing stored in the reference variable is just the location of the object in memory. So if we compare two reference variables using equals, it just simply compares the locations in memory. There may be some situations where this is what you intend to do, but typically not. Typically you want to find out if two objects are equal along some particular axis. So what I mean here is we would consider two students to be equal if they had the same name, age, and GPA. We would consider two point objects to be equal if they contain the same XY data. So the measure for equality is going to depend on what specific data is represented in the object. So to test for equality, we're going to need to define our own equals operator, the dot equals method. You might be thinking, isn't there a default dot equals operator? Yes, you don't have to define your own. The compiler is going to create one for you, just like it created a constructor for you, just like it created a toString for you. But if you remember, the default toString and the default constructor weren't that helpful. We had to override those methods to be able to give the functionality that we wanted. The same thing is true here of the dot equals method. We need to override it to give the functionality we want. So remember, when we override these methods, we have to make sure that we have the precisely same name. We have to make sure that it has the exact same return type and the exact same parameters. So just like we had to decide how to convert an object to a string, we have to decide how to compare equality. So as an example, do we compare and consider two students to be equal along only one measure? So Do we only consider students equal given the student ID, or do we require that all of the instance variables or some subset of the instance variables match? So do we have to have the ID, name, GPA, and age match, or just the student ID? So the decision of how to code this equals method is going to depend on what you intend the functionality to be and a bit of common sense. But the equals method does have a little bit of trickiness to it, and we're not going to fully talk about all the details, but we're going to show you how to do it correctly, and you'll discuss why this is the correct way to do it in a further class. So first of all, the equals method has a single parameter, and we said that to override a method, we must have the same return type, same method name, and same parameter list. So to compare the equality of two objects, you have to have two objects. The first is the implicit parameter to the equals method. So like we said, s1 dot equals, s1 will be the implicit parameter to the equals method, but we also have to pass in the object as a parameter that we want to compare it to. So why is that so tricky? You might be thinking, well, that's easy. We just declare the parameter to be the same type as the class we're using, right? So if we're going to compare two student type objects, then we're going to have a parameter of type student. No, that's not right, because the dot equals method always accepts a parameter of type object. So defining your equals method as follows would be incorrect. Public Boolean equals, all that's good. We're going to return a Boolean variable, and the name of the method is equals, but the parameter should not be of type student. So to be consistent with the Java .equals implementation and to override it, we have to accept any object. So this is a generic object as the parameter. So this is the syntax we should use when we're coding the equals method. It should be public Boolean equals, and then the type is this generic type called object. And then the name is going to be just something like other, because this is the other object that we want to compare to the implicit object. And there's a very good reason for why we have to do it this way. Like we said, we're not going to discuss all the details. Just for now, understand that this is the right way to do it. But there's a little bit more tricky stuff to talk about. So since we have to use a generic object, before we can try to access any of the instance variables or instance methods inside that object, we have to verify that the type of the object is actually right. So what we're saying is, since we are using a generic object type, it would be valid for someone to pass in a null or a string object or an array object, any object at all. So before we can attempt to use, in the case of a student, the student.getName method, we have to verify that we are in fact dealing with an object of type student. So to do this, we have to use the instance of keyword. So this is going to check to see if the type of the object matches what we expect. And if it does, then we will actually cast it into a variable of the appropriate type, and then we can make use of any of the various instance methods or instance variables. So here's an example of what this looks like in code when we override the equals method. So we would have public Boolean return type, because equals is always going to return true for yes, they are equal, or false for no, they are not. The name is equals because we're overriding the default equals method, and it accepts some object, generic object type, and we're calling it other. The first thing we have to do is to check if other is an object of type student. The way to do this is to use the keyword instance of. So it's not exactly a method, it's a keyword. So the syntax looks like this. Other, which is the name of the object parameter, other instance of, all one word, all lowercase, and then the name of the class name that we're comparing it to. So other instance of student. This is a Boolean expression. It will evaluate to true if other is an instance of student, or false if other is not an instance of student. So this is how we check to see if the generic object other is an instance of type student. If it is an instance of type student, we're going to perform a casting operation and store it into a student reference variable, a local student reference variable. So we have our object called other, and then we cast it just like we've cast integers into doubles or doubles into integers. We're going to cast this generic object into a type student and store it into this student reference variable called other stu. Finally, we are going to return this Boolean expression. ID is an instance variable for the student class. So this is going to check to see if the ID for the implicit parameter, so if we called s1.equals, this is going to be s1's ID. So is s1's ID equal to this new student object that has been passed in's ID? And if they match, then we return true. If they don't, we will return false, because this Boolean expression will evaluate to true or false depending on if these two are equal. Finally, if we have found that the generic object other is not an instance of type student, then we'll follow this else statement and we return false. Notice here, we're directly accessing the ID even though the ID is set to private. Yes, since we are inside the student class, even though we're dealing with another student object, we're still inside of the student class, and we're therefore able to access even the private instance variables of another student object.